Hello everyone. In this video, I'll discuss some key questions frequently asked in RTL and digital design interviews. One common question is, what is a reset signal? A reset signal is a control signal used in hardware systems to set digital logic circuits to a default or known state when the system is powered up. During design development, the reset signal is often activated at the beginning of a simulation to replicate real hardware behavior. In actual chip, the reset is typically triggered when the device is powered on. The reset can be active low reset or active high reset. If the reset is active low, it means that the signal is considered active when it is in low logic state or zero. When the reset is active high, it means the signal is considered active when it is in high logic state or 1. There are two types of reset signals: synchronous and asynchronous. Let's understand what an asynchronous reset signal is. An asynchronous reset signal is effective immediately upon being asserted, regardless of the clock signal. This allows hardware to reset instantly even if the clock is not running. Asynchronous resets are useful in the systems that require an immediate reset response. As shown in the waveforms here, as soon as the asynchronous reset signal a reset underscore n goes low, variable var1 is set to value 0. Asynchronous reset signals are less common in designs because glitches on the reset line can trigger spurious reset, potentially causing metastability issues within the circuit. Here is the Verilog code where we have asynchronous reset. In this always block, at the negative edge of the reset signal, if the value of reset is 0, var1 is set to 0. We can see that in this always block, the asynchronous reset signal a reset underscore n is effective independent of the clock. Synchronous reset. A synchronous reset becomes effective in the circuit only at the active edge of the clock. While the reset signal can be asserted anytime, it takes effect only when the clock transitions at the designated edge. As seen in the waveforms here, the synchronous reset goes from 1 to 0 at this point. However, its effect is seen only at the positive edge of the clock, and that's the place where van1 is set to 0. When using a synchronous reset, designs are more robust against glitches in the reset signal, as these glitches are ignored unless they coincide with the active clock edge. It is also easier to verify during timing analysis as the reset operation is aligned with the clock signal. However, the clock must be running for the reset to take effect. This is a Verilog code where we have a synchronous reset signal. At the positive edge of the clock, reset signal is checked, and if it is 0, var1 is set to 0. In general, synchronous resets are preferred unless the specific circuits demands an asynchronous reset. Another important question usually asked in the interviews is designing a rising edge or falling edge detector circuit. First, let's look at positive edge detector circuit. A positive edge detector circuit or a rising edge detector circuit is used to detect a transition from low to high or 0 to 1 in a monitored signal. Whenever this transition occurs, the detector circuit generates a short pulse, indicating the rising edge. This is the Verilog code for a positive edge detector circuit. In underscore 6 is the monitored signal where we want to detect the rising edge. To design this circuit, we delay the monitored signal by 1 clock cycle. Then we invert the delayed signal and perform an AND operation with the original signal. This way, an output pulse is generated whenever signal in underscore sig transitions from 0 to high. Here are the waveforms for the signals in this code. In the waveforms, we observe that a pulse is generated precisely at the rising edge of the monitored signal in underscore sig. Now, let's look at negative edge or a falling edge detector circuit. Falling edge detector is converse of the rising edge detector. It detects a transition from high to low or 1 to 0 in the monitored signal. To design this circuit, we delay the monitored signal by one clock cycle, and then we perform a logical AND of this delayed signal and the inverted original signal. Here are the waveforms. In the waveforms, we can observe that the circuit detects the falling edge. Inferred latch. Inferred latch is a commonly asked question in interviews. So let's understand. Inferred latch refers to the unintentional creation of latches in RTL designs. The most common cause of unintended latch inference is missing assignment to the signals in if then else and case statements. If certain conditions are not explicitly covered, the synthesizer assumes that the signal should retain its previous value, effectively creating a latch to remember the state. Here we have two Verilog codes. For the code on the left, we have complete assignment for Z, which synthesizes to a mux, while the code on the right misses the else case and results into an incomplete assignment for Z. During synthesis, the synthesizer assumes that the value of Z is to be retained, and then it creates a latch. This unintentional latch creation is referred as inferred latch. Let's understand what issues can happen due to inferred latches. Since latches store information, this can cause unintended behavior, often leading to incorrect circuit functionality if not handled correctly. In a purely combinational block, inferring a latch introduces sequential behavior that may not be intended by designer. To avoid inferred latches in the design, we can follow a few guidelines. As a best practice, while writing an RTL code, always ensure that all conditions are covered in conditional statements. For example, when using if, else, or case structures. Assign default values to signal before defining conditional logic. Taking care of these points while RTL coding, designers can avoid unintentional inferred latches during synthesis.